Alembert'S principle. It is from the Goldstein book, Classical Mechanics. So, topic number 1.4, D'Alembert's principle. Okay, see, D'Alembert principle is related to a virtual displacement concept. Okay, so what is the virtual displacement? See, a virtual displacement or infinitesimal displacement of a system refers to the change in the coordinate system of configuration. Okay, so there is some kind of the configuration, and the change in this configuration, the arrangement of the points, okay, it refers to the virtual displacement. Suppose there is an infinitesimal change in the coordinates delta Ri, okay, and this infinitesimal change in the coordinates consistent with the force and constraint imposed on the system. Constraint means the restriction. तो ये एक configuration है, is a configuration, and in this configuration there are large points or particles, is like some kind of the arrangements, and this configuration may be changed. Okay, so it is changed due to some applied force, external force, and some constraint. And whatever the change in the coordinates, whatever the infinitesimal displacement, that is refers to the virtual displacement at any given instant of time. It is a virtual displacement. These things are the abstract things, so please be alert. So this displacement is called the virtual to distinguish it from an actual displacement of the system. Means suppose this system is in a motion, so that is the actual displacement, and because this is not actual displacement, that's why it is known as the virtual displacement at any interval of time. So suppose the system is in equilibrium. So equilibrium means the total force, total external force should vanish or zero. So then the dot product of force and the virtual displacement, which is the virtual work, it should be zero. If the total force is zero, then the virtual work also be zero. It is equation 1.40. Okay, suppose we decompose this external force into two parts, this total force into two parts. One is the applied force, and second part is the force of the constraint. Constraint means restriction. So this equation 1.40 with the help of equation 1.41 becomes this. These all are the vector quantities. Okay, or okay, so this is the equation. We now restrict ourselves to the system for which the net virtual work of the forces of constraint is zero. Okay, means we are talking in that system in which this force is zero, this work is zero. Okay, the work due to the force of constraint, the virtual work due to the force of constraint. Constraint means the restriction force is zero. And we know that this condition is true only for the rigid body system. Okay, and it's also valid for a large number of other constraints. So if a particle is constrained to move, suppose on a surface, particle is restricted to move on this surface, the force of constraint is perpendicular to the surface. Okay, and the virtual displacement is the tangent to the surface. So that's why in that case work will be zero. But this will be not true if there is a friction, and especially sliding friction. If sliding friction is present, then this will not be zero. This part will not be zero. This virtual work with the constraint will not be zero. Okay. Why? Because friction is a macroscopic phenomena. And the force of rolling friction do not violate this condition. Why? Because in the case of the rolling friction, the forces act on a particular point जहाँ पे ये एक पॉइंट पे रोल कर रहा है, the system is momentarily at rest and can do no work into the infinitesimal displacement. Okay. If a particle is constrained to a surface that is itself moving in time, means this surface is also moving in time, the force of constraint is instantaneously perpendicular to the surface, and the work during this virtual displacement still will be zero. So in all these cases, work will be zero. And the work during actual displacement in the time dt will be zero. Okay. So due to all these constraints things, our equation 1.42 becomes this. So see, we discuss that the virtual work will be zero in the case of the rigid body, in the case of the friction. This is equation 1.43. Equation 1.43 is often called the principle of virtual work. Principle of virtual work. Okay. Why? See, the coefficient of delta Ri can no longer be zero. Okay. In general, this external applied force is not zero. Okay. And delta Ri are not completely independent. These displacements, these virtual displacements, are connected to the we can say that constraints. These are connected to the constraints. Okay. If we want to equate, in order to equate the coefficient to be zero, अगर ये ज़ीरो करना चाहते हैं, we must transform the principle into a form involving the virtual displacement of the qi. Means if we want to put the coefficient of virtual displacement to be zero, then we have to be change this equation into terms of the generalized coordinates. Okay, because delta Ri's are not completely independent. Okay, but qi coordinates are totally independent. So you have to be change your equation in terms of the qi, in terms of the generalized coordinate. And equation 1.43, this equation satisfy our needs in that it does not contain fi. क्योंकि जो fi था ये नहीं ले रहे हैं, इसके अंदर कंस्ट्रेंट वाला फोर्स नहीं ले रहे हैं. But the problem is that it deals only with the statics. it deals only with the statics condition. Hmm? Okay, and we want a condition involving the general motion of the system. So let's see how we will deal with this problem. Hmm? So to obtain such a principle, we use a device given by the Bernoulli and developed by the Alembert, and the device gives the equation of the motion. So see, force is related to the rate of change of linear momentum. Sometimes it is written as a P dot. Okay, so this equation can be written as Fi minus Pi dot is equal to 0, which states that the particles in the system will be the in equilibrium. So under a force equal to the actual force plus a reverse effective force, means this is the actual force and it is a reverse effective force. So instead of 1.40, we can write down our equation as Fi minus Pi dot del Ri is equal to 0. Equation 1.44. And making the same resolution into the applied force condition and the force of constraints, means put this equation into the previous one. This equation may be 1.42. So this equation becomes Fi A minus Pi dot del Ri plus work due to the constraint force. Okay, again we restrict ourselves to a system in such a system in which work done due to this constraint force will be 0. Okay, so this work done will vanish. So our equation becomes Fi applied force minus Pi dot del Ri is equal to 0. Okay, this is equation 1.45. Okay, and this equation is often called the D'Alembert's principle. Okay, this is D'Alembert's principle. So in a single statement, D'Alembert principles tells about the work done due to the virtual displacement. Okay, so this is the D'Alembert principle. So we achieved our aim. The force of constraints no longer appear, and we can drop this superscript A. Okay, so there is no ambiguity now because there is only one force, so we drop this A and we can write down directly this Fi minus Pi dot del Ri is equal to 0. Okay. Okay, so now we have to transform this principle into the terms of the generalized coordinates. Okay, so why? Because generalized coordinates are the independents with each other, okay, for all holonomic constraints. So let's transform the equation into terms of generalized coordinates. So means we have to be transform Ri into the Qi or Qj. Okay, so you know that Ri depends upon all the coordinates Q1, Q2, Q and T. The second of 1.45. Okay, we are assuming an independent coordinates and is carried out by means of the usual chain rules. Hmm? So we can express Vi with the help of the chain rule. Dri by dt is equal to C. We can write down it is as del Ri over del Q1 and del Q1 over del T plus second term plus third term and so on plus del Ri over del T last term. And because there's the first term, second term, third term, and this is we can write down as the Q1 dot. So derivative with respect to time we can represent as a dot. So it is sigma k del Ri del qk dot plus del Ri del T. Equation 1.46. Okay. So similarly, the arbitrary virtual displacement delta Ri we can express as this. Sigma j del Ri over del Qj del Qj. Equation 1.47. Okay. So there is no variation of time. Delta is involved here. Since a virtual displacement, by the definition, consider only displacement of the coordinates. Okay. So we are only considering the displacement of the coordinates. Okay. So in terms of the generalized coordinates, the virtual work becomes this. This virtual work we are transforming using 1.47 equation. So the value from the 1.47 Fi dot del Ri del Qj del Qj. So see this the summation over I and j. This whole term known as the generalized force. Qj del Qj. Equation 1.48. So Qj are called the components of the generalized force and Qj defined as this. So there are several examples, just like in a rotational motion, this torque becomes the generalized force and the theta becomes the generalized coordinate or displacement, delta theta. This is equation 1.49. Okay. The Qs need not have the dimension of the length. Okay. So the Qs not necessary dimension of the force. As I told you, that torque becomes a generalized force when angle becomes a generalized coordinate. But this Qi and Qj should always have the dimension of the work. So the this completely have a dimension of the work. Okay, work dimension, but not necessarily it is dimension of the force, it is dimension of the length. Okay, so I already told you about the example of the torque. So Qj might be torque and del Qj may be the differential angle. So Nj, the torque into the angle becomes a differential of the work. Okay. And 1.45 equation we can write down in this way. 1.45 equation, which was this. Oh, we can write down it is as pi dot del Ri is equal to the force, and force we can write down as mass into acceleration. Acceleration means velocity dot, and velocity means displacement double dot. Okay, mx double dot. So it is mi ri double dot del Ri. So this del Ri, expressing del Ri by equation 1.47 previously in terms of the generalized coordinate, we can write it down as this: mi ri double dot del Ri del qj del qj. Okay, and this relation becomes, see, this is the first part double dot, this is the second part, and you should think in terms of the total derivative. See, if we are using total derivative of d by dt mi ri dot del Ri del qj. So this total derivative change this derivative of first into second plus first into derivative of second, chain rule. So it becomes mi ri double dot, okay, first derivative, second expression as it is, plus first expression as it is, derivative of the second. So this thing, this expression we can write down in terms of this expression minus this expression is a multiple sign. Okay, this minus this. Okay, so this expression, this expression, this wala expression, convert this minus this, okay, from the chain rule. So mi ri double dot del Ri del qj is equal to sigma I d over dt mi ri dot del Ri del qj minus mi ri dot d over dt del Ri del qj, equation 1.50. Okay, so that's it. And this what is this term? What is this term? See, d over dt del Ri over del qj is nothing but del Ri dot del qj. Okay, and you can expand it in terms of the more generalized coordinate, but after all, this is what? This is nothing but del vi over del q. So we can put this into here. Okay, and we can verify that this both are equivalent expression. So we can further verify, you can verify that del Vi del Qj dot is equal to the del Ri over del Qj. Okay, as these expressions are equal, similarly these expressions also equal. You can verify yourself, and if you didn't understand, you can comment and ask. I deliberately not explaining this part. Okay, so 1.50 equation, change mi Ri double dot del Ri del Qj is equal to, after this previous 1.50 equation, this becomes the first part was total derivative term, and we are writing Vi instead of the expression Ri dot, we are writing Vi, because velocity Ri dot del Vi over del Qj dot from 1.51 equation, previous equation. Instead of terms R, I am writing in terms of the V, minus mi Vi dot del Vi over del Qj. Okay. So this second term on this equation 1.45, the equation 1.45, this equation 1.45. Okay, the second term actually we can expand. How we can expand? We can expand in terms of the energy. And see, this equation, the previous equation we are using and writing. See, this equation we are writing, be alert in each and every step, d over dt total derivative, and this expression, this whole expression is what? Del over del Qj dot sigma half mi Vi square. Why? See, just check, differentiate this term. So what will be this? Differentiation will be half as it is, mi as it is, V square will be 2Vi, and Vi will be del Vi over del Qj dot. So 2 cancel, mi Vi del V del Q. So this. Okay. So both are the same thing. Okay. So we are expressing this term in terms of the kinetic energy. It is nothing but the kinetic energy. Similarly, the second part, this minus del over del Qj sigma I half mi Vi square. Okay, because there is no Qj term in the Vi, so it will be 0. It should be 0, and the second part, this whole thing, we consider it as a Qj. Okay, so it is extra term putting by hand minus qj, uh, the bracket should be closed, del q g. Okay, so this is the extra term. It is kinetic energy. It is kinetic energy. So in terms of the kinetic energy, we can write down it is as d by dt del qj dot kinetic energy t is the kinetic energy, minus is the kinetic energy again, minus q I or j del qj is equal to 0. Okay, equation 1.5. Okay, so in the system of a Cartesian coordinate, the partial derivative of t kinetic energy with respect to the qj will be vanish. Okay, so this term will vanish. So in terms of the language of differential geometry, the term arises from the curvature of the coordinates. Okay, so in the Cartesian coordinate system, because there is a no curvature, so this part will be 0. In the polar coordinates, the partial derivative of t with respect to the angle coordinates and the centripetal acceleration will be not 0. So it will appear. So this equation 1.52 in short we can write down as d upon dt del t over del q j dot minus del t over del qj is equal to qj. This is equation 1.53. Okay, and when the forces are the derivable from the scalar potential, suppose forces we can write down as a gradient of some potential and derivable of the scalar function, then this generalized four terms qj is equal to fi dot del ri over del qj can be written as a in terms of the potential or scalar function. Okay, and we can put these things into here. Okay, so in short, this qj we can write down as a this expression is exactly the same because this is nothing but v is derivable with respect to r. So from the chain rule we can write down it is as a del v over del qj or del qi whatsoever, 1.54, and we can put this value 1.54 value into the equation 1.53 and it becomes d over dt del t over del q j dot minus del t over del q I or j, you can use one symbol, and the qj term which is minus, so minus minus plus, okay, because potential does not depend upon the qj dot, potential is only a function of generalized coordinate, so we can put by hand this term del v over del qj dot, or because anyway it is 0, so just for the symmetry we are writing it as a t minus v del qj dot minus from minus outside and again t minus v, both sides symmetry, t minus v, and it is 0. This t minus v term is a very special term. It is known as the Lagrangian. L. T minus V is known as the Lagrangian. So this equation becomes, the upper equation becomes d by dt del L over del Qj dot minus del L over del Qj is equal to 0. And this is very famous equation. This equation becomes 1.57, and this is a very famous equation. I hope you know the name. Please put the name in the comment box. And the equation is Lagrange equation of motion, Lagrangian equation of motion sometime. So it is very famous equation, and you have to deal with this equation. You will solve all the problem with the help of this Lagrangian equation of motion. Okay, so it is 1.57. We will study more about this Lagrangian equation of motion in the next videos, and there are several other videos available in this channel with very good examples of the Lagrangian equation of motion. And one additional thing I want to add, see this Lagrangian, this Lagrangian function, this Lagrangian which is depend upon the generalized coordinate q, generalized velocity q dot, and time. Okay, this remains same if we change this Lagrangian as a some additional function df over dt. So Lagrangian equation of motion becomes unchanged. This is a very important result. Okay, both Lagrangian L and L prime will give you the same equation of motion. Okay, and it's only for the conservative system. The 1.56 equations is a suitable choice of the conservative system. Okay, so that's all about the D'Alembert principle and the Lagrangian equation of motion. Okay, so we started very neatly and cleanly from here, from D'Alembert principle, and we started D'Alembert principle from very basic concept of the virtual displacement. Okay, if you have any kind of doubt, you can comment. Okay.